Hey everyone, and welcome back to AI.Code.Cast. We're diving deep into a classic coding problem that's a real brain teaser. Find the winner of the circular game. It sounds super simple at first, but trust me, there's way more to it than meets the eye.
Yeah, it's definitely one of those problems that seems deceptively straightforward, but it kind of quickly reveals all these layers of complexity once you start exploring the different approaches to solving it.
So let's set the scene. Imagine you and your friends are sitting in a circle, and you decide to play this game right, where you eliminate like every kth person.
Oh, like a much more intense version of Duck Duck Goose.
Exactly. With much higher stakes. Only one person gets to stay in the circle. So the last one standing wins. The challenge is, given the number of friends in the circle N and the elimination step K, can we predict who the winner will be?
And that's where the whole algorithmic thinking comes in. We need a way to model this elimination process efficiently.
So let's break down the rules a little bit further. We've got N friends in the circle numbered from 1 to N. We start counting at friend number 1 and move clockwise, eliminating every kth friend. But here's the catch: the counting wraps around the circle.
It's like playing a never-ending game of tag where you skip over people until you land on the one who's it.
Exactly. And after each elimination, we continue the count from the person immediately next to the one who was just eliminated. So it keeps going and going until only one person is left.
I think it's a good time to address a common pitfall people might encounter right off the bat. What happens when our counting reaches the end of the circle?
Ah, yes. That's super easy to accidentally go out of bounds if we're not careful. We need to make sure our logic accounts for that circular wraparound. It's like those old school arcade games where if you go off one side of the screen, you reappear on the other.
Exactly. That's where the whole concept of a circular array comes in handy. It's a data structure that basically lets us seamlessly loop back to the beginning once we reach the end. It's like the perfect representation of our circle of friends.
Okay, cool. So we've got our rules, our circular array. Where do we even begin to solve this?
Well, a good starting point, like with many coding problems, is the brute force approach.
You mean just like simulate the whole game step by step?
Yeah, exactly. It might not be the most efficient way, but it definitely helps us visualize the problem and understand the core logic.
All right, let's give it a try. So if we were to manually play this game, how would we actually keep track of who's in and who's out?
We could use a simple list to represent our circle of friends. So initially, this list would contain numbers from 1 to n, representing each friend.
Okay, so as we eliminate someone, we just remove their number from the list.
Exactly. And then we need to adjust our starting position for the next round, making sure we continue counting from the person next to the one who is eliminated.
Makes sense. So we keep doing that until only one number is left in the list, and that's our winner. But I can already see how this could get pretty messy and inefficient.
Yeah, especially if we have a really large number of friends. Imagine having to rearrange a physical list every time someone gets eliminated. Lots of shuffling. Potential for errors.
Right. And from a coding perspective, removing elements from the middle of a list repeatedly can get computationally expensive.
Yeah, exactly. That's where the concept of time complexity comes in. So the brute force approach has a time complexity of ON2, meaning that the time it takes to run basically grows quadratically with the number of friends.
So if we have 10 friends, it might take a short amount of time. But with 100 friends, it could take much, much longer. Not ideal. What about the space complexity?
Well, since we're only storing the list of friends, the space complexity is ON, which isn't too bad.
So this brute force approach is like a trusty old car. Gets you there, but it's a bit clunky and slow. We need something a bit more streamlined, maybe even a sports car, to really speed things up.
I like that analogy, and thankfully there are other more efficient approaches we can explore. Perhaps a queue-based approach could be our sports car in this scenario.
A queue, huh? I remember those from my data structures class. They're like aligned at the store, first in, first out. But how could we even apply that to this problem?
That's a great question. Let's take a closer look at how a queue might help us simulate this circular elimination process more efficiently in the next part of our deep dive. Welcome back to AI.Code.Cast. So let's pick up right where we left off with the find the winner of the circular game problem.
Yeah, we were exploring that brute force approach using a list, which kind of felt like using a horse and buggy in a Formula One race.
A very apt comparison. While the list-based approach is great for visualization, its ON2 time complexity can become a real bottleneck, especially for large inputs.
So you mentioned a queue-based approach could be a more efficient solution. I'm
Yeah.
curious to see how that plays out.
While Q, with its first in, first out nature, is surprisingly well suited for simulating this elimination process. Remember, it's like a line at the store. The first person in line is the first one served.
Right. So how do we translate that to our circle of friends?
Imagine we start by putting all our friends numbered 1 to n into a queue. This queue represents our circle, with the front of the queue being the starting point of our game.
Okay, so instead of like physically removing elements from a list, we're using the queue structure to kind of manage who's next in line for elimination.
Precisely. We can simulate the whole elimination process by just cleverly manipulating the queue.
All right, walk me through this manipulation.
Yeah.
How do we actually use the queue to eliminate every kth friend?
So for each round, we'll dequeue the first K1 friends. So these are the friends we're essentially skipping in our counting process. But instead of discarding them, we enqueue them right back to the rear of the queue.
So it's like those friends get to rejoin the back of the line after being temporarily skipped. I like it.
Exactly. And after doing this K1 times, the friend at the front of the queue becomes the Kth friend, the one who's destined for elimination.
And to eliminate them, we simply dequeue them from the queue, shrinking the circle. It's like they've been tagged and are now out of the game.
Exactly. We then just repeat this process, skipping K1 friends and eliminating the next K friend until only one friend remains in the queue.
This queue-based solution definitely feels way more elegant than that brute force approach. What about its time complexity?
So the time complexity of this approach comes down to UNC, which is a significant improvement over the ON2 of the list-based approach. And this is especially noticeable when K is small or constant.
So if the elimination step K is relatively small, this solution becomes really efficient.
Absolutely. And the space complexity remains ON since we're still storing all in friends in the queue at the beginning.
So we've traded a bit of space for a significant gain in time.
Mm.
But is this the best we can do? Are there even more efficient solutions out there?
There is one particularly fascinating solution that completely bypasses the need for simulating the game step by step. It directly calculates the winner's position using a clever mathematical formula.
Hold on, a mathematical formula. You're telling me we can solve this problem without any loops or queues? I'm intrigued, but also a little skeptical.
It does sound almost magical, doesn't it? But trust me, the math behind it is quite elegant. We'll dive into the details of this mind-bending solution in the next part.
Welcome back to AI.Code.Cast. I'm still trying to wrap my head around the idea that we can solve this, find the winner of the circular game problem with just pure math.
It's definitely one of those solutions that make you really appreciate the power of mathematical insights when it comes to algorithm design. It's like finding a shortcut through a really dense forest.
A shortcut that bypasses all that simulation and data structure stuff we were discussing. I'm all ears. Let's unravel this mathematical mystery.
Okay, so the core of the solution lies in really understanding how the winner's position shifts with each elimination. So imagine we've already solved the problem for N1 friends.
Okay, so we're assuming we know the winner's position if there was one fewer friend in the circle.
Gotcha.
Exactly. Now let's add that nth friend back into the mix. What happens to the winner's position?
Well, it would seem like the winner's position would shift forward by K positions since we're eliminating every Kth person. You're on the right track. But we got to remember that our circle wraps around. So if adding K to the previous winner's position takes us beyond the end of the circle, we need to loop back to the beginning.
Ah, that makes sense. So it's not just a simple addition of K, but rather an addition followed by a modulo operation to handle that wraparound.
Precisely. The modulo operator, denoted by the percent sign, gives us the remainder after division. It's perfect for ensuring we stay within the bounds of our circular array.
Okay, cool. So we're adding K and then taking the modulo with the total number of friends.
But how do we even get that initial winner's position for N1 friends? It feels a bit like a chicken and egg situation.
That's where the iterative part comes in. So we start by calculating the winner's position for a circle with just one friend, which is trivially position 1. Then we use our formula to iteratively calculate the winner's position for increasing numbers of friends from 2 to n. So we're like building up the solution step by step, leveraging the previously calculated winner's position to find the next one, kind of like a domino effect, each domino representing the winner's position for a specific circle size.
That's a great way to visualize it. Now let me present the formula we've been building up to. It looks like this. Winner n k equal s k, winner n1 k plus k %.
Wow, that's surprisingly concise considering all that logic it encapsulates. And you said this is like the most efficient solution.
Absolutely. So the time complexity of this approach is just O(n), as we only need to iterate through our formula n times. And since we're not really using any extra data structures, the space complexity is a beautiful O(1), meaning it uses a constant amount of memory regardless of the input size.
So we found a cheat code for this problem.
Yeah.
But are there any like drawbacks to using this mathematical approach?
Yeah, one potential limitation is that this solution is very specific to the rules of this particular game. It kind of exploits a pattern that might not hold true for other circular elimination problems with slightly different rules.
So it's a highly specialized tool, perfect for this job, but might not be as versatile as other approaches.
Exactly. And while the formula itself is concise, understanding the intuition behind it might require a bit more mathematical reasoning compared to the simulation-based approaches we discussed earlier. It might not be as immediately intuitive for someone who's not as comfortable with modular arithmetic or like recursive thinking.
It's like having a super fast race car. Incredibly efficient, but requires a skilled driver to handle it effectively.
A great analogy. Ultimately, choosing the best solution depends on the specific constraints of the problem and the trade-offs you're willing to make.
Well, there you have it, folks. We journeyed through 3 distinct solutions to find the winner of the circular game problem. From the intuitive but inefficient brute force approach with its lists, to the elegant queue-based solution, and finally to the mind-bending efficiency of our mathematical shortcut.
And each approach offered its own insights into the problem, really demonstrating that there are often like multiple paths to a solution in the world of algorithms.
It's like having a toolbox full of different tools, right? The best tool for the job depends on the task at hand.
Exactly. I hope this deep dive has not only equipped you with the knowledge to tackle this specific problem, but has also broadened your perspective on algorithmic thinking and problem solving in general.
And that wraps up this episode of AI.Code.Cast. We'll catch you next time for another exciting exploration into the world of algorithms. Until then, happy coding.